All right, I will begin again. So I want to talk to you now about electromagnetism in differential form. And so I guess I probably should explain essentially what's going on here is we're going to use Minkowski space. What is Minkowski space? Well, aka spacetime. So you work in R4, all right, in R4 where one of the coordinates is time, all right. Now, so in short, you're so like zero. Let me just kind of break it down real quick. Zero form would be like a function of t, x, y, and z, right? A one form would be something like, you know, alpha dt plus like a dx plus b dy plus c dz. So we'll use t as the fourth coordinate, okay? A two form would look something like, you know, I say alpha 1 dt wedge dx, alpha 2 dt wedge dy, alpha 3 dt wedge dz, let's say plus maybe beta 1 dy wedge dz, beta 2 dz wedge dx, beta 3 dx wedge dy. Right. Three form on R4 would look something like, well, let's see here. Goodness, I haven't thought about this one. I guess you've got alpha 1 dt wedge dy wedge dz, alpha 2 dt wedge dz wedge dx, alpha 3 dt wedge dx wedge dy, and then of course you got your, let's say, gamma, or I guess maybe I'll use a g. I mean, whatever. I just need a letter. Dx wedge dy wedge dz. It'll be a three form, and well, the four forms. There's just one of those guys. Something like h dt wedge dx, wedge dy wedge dz. All right. So there you go. This is your life. If you want to talk about differential forms on R4 in space-time. So the set of zero forms is one-dimensional at a point. At a point, forms are one-dimensional. Of course, so at a point, the set of one forms is four-dimensional. The set of three forms is four-dimensional. The set of two forms is six-dimensional. There is a way we can interface. You can use quote-unquote 3+1 formalism, a mixture of our three-dimensional vector calculus and our four-dimensional space-time formalism. Some things kind of present themselves here to be somewhat obvious. So in particular, this is like alpha dt plus really the work form, right, of ABC. See that? And this guy here we could rewrite as like dt wedge the work form of alpha 1, alpha 2, alpha 3, right? For the first three terms, and then the flux form of the vector field beta 1, beta 2, beta 3, right? Now be careful. Be careful. It's the component functions here. They're not like our component functions in R3, our component functions in R3 are just functions of x, y, and z. But the component functions here are in principle functions of x, y, z, and t. There could be a time dependence. And this one, we would have something like, you can pull the dt out, and basically you got like dt wedge the flux form of the vector field alpha 1, alpha 2, alpha 3, right? And then plus g times dx wedge dy wedge dz. All right, great. There is a concept of Hodge duality on R4 as well. So, you know, on page 275 have like basically a nice, you know, quick list of some of these. I'll just write down a few. So like the Hodge dual of 1 is dt wedge dx wedge dy wedge dz. The Hodge dual of like dx wedge dy is actually minus dz wedge dt, or you could write it dt wedge dz, right? And on the flip side, the Hodge dual of like dz wedge dt is equal to dx wedge dy. So apparently the Hodge dual of dx wedge dy is what? Looks like we get a minus this time. Now, in the three-dimensional case, the Hodge dual is just back where we started again. But here, there's a sign that enters in. The Hodge dual, it turns out that turns out to be, I think that's the case for all the forms. For like, here's the top form. This one, Hodge dual is to -1. So you can see from that, the Hodge dual of the top form, or the Hodge dual of 1 gets you back to minus itself. So it looks like Hodge dual squared is -1 in this context. I guess I should check the three forms. Looking at my chart, the Hodge dual of, well, I guess we can figure out if I just write down one. The Hodge dual of dx wedge dy wedge dz is minus dt. And I'm also told the Hodge dual of dt is minus dx wedge dy wedge dz. So if I take the Hodge dual of dx wedge dy dz, I get minus the Hodge dual of dt. Maybe that goes back to +1 actually. Yeah, because if I take the Hodge dual of dt, what happens? Pull the minus out, right? But then the Hodge dual of dx wedge dy dt is minus dt, so you get minus a minus dt. Aha. So I think what's going on here is the Hodge dual times the Hodge dual is -1 to the p + 1, perhaps? Looks like it depends on the degree of the form, because for 0 form and for 4 form, it's squared to -1. For the 2 form, it squares to -1. But for the 1 form and for the 3 forms, it's Hodge dual of, all right, great. All right, so, great. What is the Hodge dual? How does it actually work here? What's the Hodge dual of like dt wedge omega a vector, let's say, plus phi the B vector. What would that be? Let's see if I've written enough to figure that out. The Hodge dual of like dt, so the Hodge dual of dt, so like the Hodge dual of dt wedge dz, right, is minus dx wedge dy. So that basically shows you that the z component in the flux form, I mean the work form, is going to transfer to like minus the z component in the, so I think what's happening is you're going to get minus the flux form of A. And let's see, for the B one, if you look at that, like dx wedge dy is going to that. So it's actually going to end up being plus t wedge, if I'm not wrong, plus dt wedge the work form of B. So that's like Hodge duality for two forms is doing something like that. It's switching the temporal part of the two form to the spatial part of the two form, and vice versa. It's like flipping back and forth the spatial and the time space part of it. And the Hodge dual of the, what's the Hodge dual of alpha dt plus the work form of a vector field A? Well, the Hodge dual of the dt, I guess I haven't written it down. Oh, here it is. So that's going to give you minus alpha dx wedge dy wedge dz. And let's see what happens with the work form. Like, what's the Hodge dual of dx? Where's that going? Did I write it down anywhere? What was the Hodge dual of dx? I guess I didn't write it down. The Hodge dual of dx is like minus minus dy wedge dz wedge dt. So that looks like it's going to give us a minus the flux form of A wedge dt. Okay, anyway, so there's some sample Hodge duals. Now, what does the exterior derivative look like in this context? Like it brings in time derivatives as well, all right? Time derivatives enter the story here now. So like if I take the, first of all, for a function, start there, right? So what I'm trying to do is build up for you how we can use space-time to write equations of vector calculus that involve time derivatives in a natural language in the 3+1 formalism. We're getting there. So df is partial f partial t dt plus partial f partial x dx plus partial f partial y dy plus partial f partial z dz. But what is that? Well, what you're looking at, of course, is partial f partial t dt plus what? Plus the work form of the regular gradient of f, if you will. Okay? And great. And let's see here. So what would happen if I calculate the exterior derivative of like a you know, a two form, or no, one form. So I have something like alpha dt, right, plus the work form of ABC. How's that go? So the time derivative of alpha, irrelevant, right? So you're just going to get the work form of the gradient of alpha wedged with dt from the spatial derivatives there. That's it for this one. This one, from the spatial part of the derivatives, we get exactly the flux form of the curl of ABC for the same reasons we did in the three-dimensional context. But there's more, right? Because there's also plus, I guess I'll just have to write it out, because you've got like partial A, partial T, dt wedge dx, plus partial A, partial B, partial T, dt wedge dy, partial B, partial C rather, partial C, partial T, dt wedge dz, right? Because remember, the omega ABC is ADX plus BDY plus CDZ, right? That's what this means. So the spatial derivatives of this just give us the curl, but now there are these entering in. What's this? Well, if you look at this for a second, what you're looking at is you're looking at the work form of, no, yeah, my bad. So you're looking at dt, right, wedged with what? Partial A, partial T dx, partial A, partial B, partial T dy, plus partial C, partial T dz, right? That's exactly dt wedged with the work form of partial, I guess I need to come up with a name for this. I really should just call this thing, sorry, it was poor planning on my part. Let me call this whole vector here A vector, okay? Then this is partial A, partial T. So just to rewrite it cleanly, we have the exterior derivative of a function alpha times dt plus the work form of a vector field A. It's the work form of the gradient of the scalar function wedge dt plus the flux form of the curl of A plus dt wedge the work form of the time derivative of A. So we can actually do better, see, because these two terms here can be combined, right? And the fact that the work form is a linear map, we can combine it, and we can either keep the t second or keep the t first. I don't know, whatever. I'll keep the t first. I'll keep the t second. If I keep the t second, this is going to give me omega of the gradient of alpha minus partial A, partial T, wedge dt, plus the flux form of the curl of A. So what I'm trying to get at here is the exterior derivative of a one form on space-time. It builds both time derivatives of the vector field that underlies the form, and also time derivatives and the curl of the vector field that underlies the form. And it naturally links them to the gradient of the scalar function, that whatever the purpose of that would be. All right. And okay, so next, how about two forms? What's that look like? What's the exterior derivative of a two form? What happens when we exterior differentiate, something of the form like, let's say dt wedge the work form of, I'll say A, plus the flux form of, let's say B. Maybe instead of using A, I'll use an E here for a change of pace. So again, what you're going to get is that when we exterior differentiate the time component, the dt wedge dt is 0, so only the spatial derivatives matter. You get dt wedge the flux form of the curl of the vector field E, for the same reasons we did in 3 dimensions. But then you get plus, you know, this guy here. Well, on the one hand, you've got well, the same calculation that we had before happens up here. Basically, we end up with oh, fine, I'll write it out. The one thing we get, of course, is that we get the divergence of B, right? dx wedge dy wedge dz. Remember, we're taking the wedge product. The differential exterior derivative of a 2 form is a 3 form. So in particular, that puts us in context with the divergence for that. But there's another piece here, which is, of course, partial b1 partial t dt wedged with dy wedged with dz plus partial b2 partial t dt wedged with dz wedged with dz with dx, and then plus partial b3 partial t dt wedged with dx wedged with dy. That we can write more cleverly as simply the work form of the partial derivative of the vector field B with respect to t, right? No, my bad. Not that. Not that. Factor the t out. You got dt wedged with what? The flux form, actually, of partial B partial t. Because this guy gets paired with these, this gets paired with those, this gets paired with these guys. That's the flux form map. So so that's the exterior calculus on space-time in a nutshell. Of course, we can also talk about you know, integration of, you know, forms on curves or surfaces as appropriate. But let me see. Let me just get to the point here. I'm going to erase. I think I need to erase all this over here now. So now I will introduce you to the players and the game, which is electromagnetism in R4. All right. So like, why is there an electric and magnetic field? Well, the electric and magnetic field, from the viewpoint of physics, exist because there is current, electric current, and electric charge. And whenever you have current and charge, then Maxwell's equations govern how the electric and magnetic fields interact on the current and charge, according to several differential equations which are known as Maxwell's equations. But the source, if you will, of the reason that there's electric field and magnetic field is ultimately the existence of what you might call this J mu, which is by definition rho and J. So this is like dq dv, the charge per unit volume, and this is a current density, which will be less familiar to you even if you had the second semester physics, right? I'll just tell you that. And on the other hand, if you look at the covariant current, it's minus rho comma J, because we do the raising and lowering of indices here with respect to the Minkowski metric, which has a -1 and then 1, 1, 1, 1 down the diagonal. Now, so getting to the point here, we can define a current one form, J, as minus rho dt plus the work form of the current density. That's the so-called one-form current. And the Hodge dual of the one-form current is on the next page, which I will find eventually. So the Hodge dual of this guy is rho dx wedge dy wedge dz minus the flux form of the current density wedged with dt. All right, well, these may be relevant as we go on. Now, the cool thing is, one of the really neat things about electromagnetism is, well, maybe the neatest thing about it is it's actually what's called a gauge theory. And so a gauge theory is a theory in which the fields can be built from potential functions. And so in particular, we introduce something called the one-form potential A, which I'll just get straight to the point here. It's minus V dt plus omega sub A. So here V is the voltage function, which you might have heard about, and A is the so-called vector potential. All right. So the voltage we study in second semester physics. The vector potential, if we had a junior level class in electromagnetism, we'd study it there. So the curl of the vector potential gives you the magnetic field. Yeah, more on that in a second here. But the pullback of this one-form potential is what? Not the pullback, my bad. The Hodge dual of A, I say here, is just V dx wedge dy wedge dz minus the flux form of the vector potential wedge dt if you're interested. All right, so there we go. Fun formulas. All right. So these are all definitions, all right? Definition. I'm not deriving anything. This is a definition. And I will freely admit this won't make sense to you unless you've had a bunch of physics. Not entirely, anyway. But hopefully at the end of it, you can kind of appreciate what's going on. Another definition. Okay. Another definition, we can define what's called the Faraday tensor. The Faraday tensor is actually a two-form, and the Faraday tensor looks like this. F equals to the work form of the electric field wedge dt plus the flux form of the magnetic field B. I guess I should admit to you, we call E the electric field, we call B the magnetic field. All right? They're generally functions of space and time. And so if you look at this in terms of components, the way it looks like is this, Ernesto. It's an antisymmetric tensor. It's got minus E1, minus E2, minus E3 up here. It's got these components over here. And it's zeroed down the diagonal because it's antisymmetric. And you've got like B3 is here, and minus your B2 is there, and this is your B1. It's antisymmetric. So there you go. These are the Faraday tensor is a two-form on R4, which has 6 independent components. 3 of them go to the electric field, 3 of them go to the magnetic field. So the Faraday tensor naturally couples, if you will, the electric and the magnetic fields into one overarching object. The Hodge dual of the Faraday tensor is actually the flux form of the electric field minus the work form of the magnetic field wedged with dt. So you see that the Hodge duality, it kind of flips the electric and the magnetic field. It's not quite what it does, though, because as you can see, like, yeah, E has gone to B, right? But B, well, there's a minus here, right? So it's not just flipping E and B. There's an asymmetrical minus in all this, okay? You can study the interchange of electric and magnetic field in the abstract. It's called something called complexion. There's a page or two on it in Misner, Thorne, and Wheeler's gravitation book. What's not in that book? Good grief. Anyway, okay, so some equations. So one equation you could look at would be the exterior derivative of the current density. And that equals to 0 is interchangeable with the equation that the partial derivative of charge density with respect to time plus the divergence of the current density is equal to 0. So this equation I would say boxed, but that seems a little generous. That is conservation of charge. What that is saying is that if you have a region, whatever change in the charge per unit volume there is, well, that has to be balanced by the flow of current out of the region. So this actually would describe like the flow of charge out of the region in terms of a current. So that being 0 is conservation of charge. That's a basic physical principle. Conservation of charge is rudimentary to electromagnetism. So whatever else we do with these equations, it had better imply that. We had better have that the Hodge dual, the differential exterior derivative of the one-form current, well, I guess this is three-form current, but anyway, that has to be 0. Now, the beautiful thing is that dA is equal to, let me do it up here. I don't think we need all this. I'm just going to erase that a bit. All right. Whew, got to wrap this up, otherwise I'm going to be burnt out for complex. My goodness. It's for a good cause, I suppose. So the exterior derivative of A is actually equal to the Faraday tensor, all right? Since there's a couple definitions in play here. The electric field relates to the potential according to this, minus the gradient of the voltage function, minus the time derivative of the vector potential. And on the other hand, the magnetic field is just the curl of the vector potential. So to see that what I wrote in blue is legitimate, you just have to sort through. So basically this right here, in some sense these are definitions. These really, I don't know, in some sense you could say these define the voltage and the I don't know what's the right thing to say is basic here. I'm sorry, I haven't thought about it enough lately. But this is the relation of the electric field and the vector potential and the voltage function. And on the other hand, we can take the exterior derivative of a one-form as I described over on the other board, right? And so the exterior derivative of one form right here, it gives us these terms, right? So if you just follow my calculation over there, if we take the exterior derivative of minus v dt plus omega a, what's it equal to? It's equal to, the work form of what? Minus the gradient of the scalar. V is equal to alpha is equal to minus v, right? Alpha is equal to minus v in my language, and then minus partial a partial t, right? And then what? Plus dt, wedge the flux form of the curl of A. That's just calculus, right? But if you accept what I boxed as the definitions of the electric and magnetic fields, if you like, well, what's this? That's E, and that is B, right? And our definition of the Faraday right here, and I've lost a wedge dt here, right? So that is exactly, wait a minute, there's no dt there. My bad. I looked, there's no dt there. So I've put a dt where it doesn't belong, and And I've neglected one where it does belong. So here we go. That's better. Anyway, that is literally the Faraday tensor. Okay? So from one form potential, the exterior derivative of it, it will generate the electric and magnetic fields. If you give me a one form potential, then that uniquely specifies electric and magnetic fields. However, that's not to say that the one form potential is uniquely specified, because of course the d squared is 0. So I can always take the one form potential and I can add an exact form to it, and that wouldn't change the electric and magnetic fields which are derived. This is an example of what's called gauge freedom. But anyway, this is really not helpful or needed. Let's get that out of the way. I probably shouldn't have erased the bottom one there. So let me get to the point here. Here it is. Here's the point. The grand finale. df equals to 0. And the derivative of the Hodge dual of f equal to mu naught times the Hodge dual of the four-dimensional current. These are two-form equations. All right. These two equations I just wrote down are Maxwell's equations in differential form. So when we look at the exterior derivative of the Faraday tensor, it picks up derivatives of the electric and magnetic field both at once. And separately too. There's like two pieces, because when we took the derivative of a two form, what happened? How did it go? Like, what does that look like? Right, there was a piece that is, let's see, where's my two form derivative? This one, right? So when I take the exterior derivative of a two form, it gives me a three form where on the one hand I'm getting the curl of the piece that's in the work form, right? I'm also getting the divergence of the thing that's in the flux form, and I'm also getting this thing here, right? So I guess if I had taken my, I really should do an extra step here, right? dt wedge what? The flux form of what? It's really the flux form of the curl of the E plus partial B partial T, isn't it? And then plus the divergence of the B, dx wedge dy wedge dz, yeah? See, because I can take these two terms and put them together. So think about it then. If we're taking the exterior derivative of the Faraday tensor, right? What are we getting? On the one hand, so if the exterior derivative of this, if the exterior derivative of this, and you can think of this as being, well, it's almost right. This is almost the Faraday tensor. I'll put some quotes on it. It's almost the Faraday tensor because I need to, all right, I switch the order of that. And that actually matters because it's going to put a minus here, which is relevant. But essentially, oh, fine. Well, anyway, so this has to be 0, and that has to be 0. So the exterior derivative of the Faraday tensor vanishing gives me two partial differential equations in vector calculus of 3 dimensions. Well, time varying vector calculus of 3 dimensions. And what are those equations? They are that, oh, I guess I didn't make a sign error. Anyway, here it is. The curl of E plus the time derivative of B is equal to 0, and also the divergence of the magnetic field is 0. The first equation there is known as Faraday's law, and the second is known as the no magnetic monopoles. If there was magnetic charge, that would be non-zero, and these would be different. But anyway, it's not. And this one, when you do the same thing for the Hodge dual of the Faraday tensor, this ends up giving you that the curl of the magnetic field is equal to like mu naught J plus like partial E, partial T, I think, in my current formalism. There's some dimensional constants missing in this derivation because there should be. I've set C equals to 1, and when I set C equals to 1, it misses some things, okay? But yeah, so this is one of the equations in here is that, and the other one is that the divergence of the electric field is equal to the charge density rho. So the top equation there is called Ampere's law with Maxwell's correction, and the bottom is called Gauss's law. So this one equation gives you both of these. This one equation gives you both of those. And why is charge conserved? Why would the exterior derivative of, so check this out, right? If this is true, then the exterior derivative of like this is equal to d of 1 over mu naught, right? The exterior derivative of the Hodge dual of Faraday, right? Which of course is d squared, which is 0, so conservation of charge is implied by that equation, right? Also, this equation right here comes for free as soon as you're talking about a theory of potentials. See that? If I say dA is equal to F, what's that tell me? That tells me d of dA is equal to dF, which makes dF automatically 0. So that equation being 0 is kind of for free once you're working with the potential theory. This one, on the other hand, is really where the sources, the current density and the charge density, enter in and give you what your electric and magnetic fields are. Now, to actually solve these, it's a complicated business. I mean, a physicist will spend many courses just on solving these equations. We're talking like many courses, all right? And that's just the classical theory too, because you have to talk about like how do you think about these things in conjunction with quantum mechanics, and you know, there's a lot. But also, this is exciting for me in terms of it's the first example of an interesting gauge theory that we have. You can understand all of this in terms of the theory of fiber bundles with a principal gauge group where the gauge group is U1. There's a mathematician slash physicist, Weil, who found these things in like 1919 in a kind of funky way, and then in a pretty good way in 1929. And then the theory of the general gauge theory for non-abelian groups was discovered by others in like I want to say the 50s. Udiyama and Yang and Mills, of course, for SU2, a non-abelian gauge theory. And so it turns out that the way to understand gauge theory in the abstract is very much with differential forms. You essentially need to find a principal fiber bundle with the gauge group, and the connection on that fiber bundle turns out to be essentially analogous to this one form. That's actually the pullback of the one form on the fiber bundle, and like the particular way it transforms is exactly the way a local connection has to transform on a principal fiber bundle. These things really only came to light in the early 70s or so. I'm not sure how, somebody here or there might have understood it before, but they were not widely known in the early 70s. My advisor found them, understood it a couple of years before most people, and because he had some like postdocs from Princeton visiting the school, and he's like, oh, it's just the blah and the blah, and they're like, it's the what? So he said for a brief time he was ahead of the curve, but you know, mathematical physics has gone far beyond that. But the gauge theory, this is the first and most basic example of a gauge theory. So, which is, you know, one of the things I'm interested in. I guess that's it for this course. Well, thanks.